Welcome to the Deep Dive. Today, we're plunging into the absolutely fascinating yet intricate world of radio frequency technology.
It really is something else.
Just stop for a second and think about how profoundly we rely on sending information through the air. I mean, from your casual phone calls to your home Wi-Fi, the satellite TV you watch, and even the GPS that guides your drive.
It's everywhere. Completely ubiquitous.
It all hinges on incredibly sophisticated, unseen devices that send and receive radio waves. But have you ever really stopped to wonder how they actually work?
Yeah, how does that little box actually do that?
Exactly. How do we take a human voice or a complex video signal and effortlessly shoot it across miles, even through space, and then perfectly reassemble it on the other side?
It seems almost magical sometimes.
That's our mission today,
Yeah.
to unpack the secrets of transceivers, those unsung heroes of modern communication that are constantly connecting our world.
And it's quite a story. It's an area where the fundamental laws of physics meet incredibly clever engineering, a constant intricate dance between signals and noise, efficiency and fidelity, all happening at speeds and scales our everyday senses can barely comprehend.
So, not simple then.
Not simple at all. The deep dive today is heavily informed by a foundational academic text.
Which basically translates to Transmitting and Receiving Devices by V.A. Romanyuk from 2013, published by MIET, a leading National Research University in Russia.
Okay, so a solid academic source.
Oh, absolutely. It's truly a goldmine of foundational principles, technical requirements, and the functional elements that explain how radio transmitters and receivers are not just built, but how they perform the amazing physical processes happening inside them and what crucial components make it all possible. It lays it all out. So, get ready to discover some surprising facts, understand the genius behind these devices, and gain a real shortcut to being truly well-informed about the technology that connects virtually every aspect of our modern lives, often without us even realizing the incredible complexity involved.
Okay, let's unpack this. The core purpose. Why we need transceivers. All right, to really start our deep dive, let's establish the fundamental problem these devices are designed to solve. Why can't we simply shout into a microphone, convert our voice into an electrical signal, and have that signal travel effortlessly for miles or even across a city? It seems like it should be simpler than it is. That's a great question, and it immediately gets to the heart of the physics behind all radio systems. Our video signals, things like human speech, which ranges around 3 to 3.5 kilohertz.
Pretty low frequency then.
Very low. Or music, which covers maybe 20 to 20,000 hertz, or even older broadcast television signals spanning from 0 up to 6 megahertz. These all exist at very low frequencies in the electromagnetic spectrum. The fundamental, unavoidable challenge is that antennas, the devices that actually convert electrical signals into radio waves and vice versa, are only efficient if their physical size is comparable to or larger than the wavelength of the signal they're trying to transmit or receive.
Comparable in size to the wavelength. And that's where the scale becomes truly mind-boggling, isn't it? For those low frequencies, the wavelengths must be enormous.
Precisely. Enormous is the right word. To give you a vivid example, for a typical audio signal, like your voice, the smallest wavelength can literally be 100 kilometers.
Wait, 100 kilometers? That can't be right.
It is. Imagine trying to build an antenna that's 100 kilometers long just to transmit your voice, or even a modest video signal. It's simply not feasible in any practical sense.
Okay, no 100-kilometer antennas. Got it.
This physical limitation is what directly drives the entire design and incredible complexity of radio transceivers. We simply can't efficiently launch these low-frequency signals into the air directly.
So that's the core problem. And this is why we need to create what's called a radio signal, a concept that is absolutely central to this entire deep dive. It's about somehow packaging our message, right?
Yeah.
Making it compatible with the airwaves.
Exactly. Packaging is a good way to think about it. To transmit effectively and practically, we have to move the video signal spectrum much, much higher up the frequency axis.
Higher up? How much higher?
We're talking shifting it into the tens, hundreds of megahertz, or even gigahertz range. This is the realm where antennas can be of practical, manageable sizes, meters, centimeters, or even millimeters long.
Like the antenna on your phone or your Wi-Fi router.
Exactly, the kind you see everywhere. The core concept behind this vital shift is called modulation. This is the ingenious process where we systematically alter a high-frequency carrier wave with our low-frequency information.
Okay, modulation. Break that down a bit.
Think of that carrier wave as a powerful high-speed train, maybe, or a massive ocean wave. It has lots of energy and travels far. Modulation is how you load your delicate information, your voice, your data, onto that robust carrier.
So the information rides the wave.
It rides the wave, exactly.
Yeah.
This allows it to travel long distances without getting lost or dissipated. Without modulation, long-distance wireless communication as we know it simply wouldn't exist. It's that fundamental.
So what does this all mean for the big picture of communication? It means we fundamentally need two primary, highly sophisticated components for any functional radio system. Something to send that carefully packaged signal,
Right, the sender.
and something on the other end to catch it and unpack the original message. You truly can't have meaningful communication without both.
That's absolutely right. We have transmitters and receivers, each with distinct but complementary critical functions. Transmitters take your original low-frequency information, modulate it onto a high-frequency carrier, amplify it, and then blast it out into the air.
Okay, send it out strong.
And receivers, on the other hand, do the exact opposite. They diligently pick up that often incredibly weak, high-frequency radio signal, strip away the carrier, that's demodulation, and meticulously extract the original low-frequency information.
Got it. So it's a complete unbroken communication loop facilitated by these two distinct but intricately connected devices. Two, the transmitter, shaping and sending the signal. Let's start with the sending side of that communication loop then. Once we understand why we can't just send raw voice signals, what's the main job of a radio transmitter? What are its primary functions to get our message out there effectively?
Okay, the sender. Well, the foundational text we're diving into today clearly identifies three primary tasks for any radio transmitter, whether it's for a simple walkie-talkie or a complex satellite system.
Three main jobs. What are they?
First, it needs to be capable of generating high-frequency electromagnetic oscillations. This is your carrier wave, and it must be incredibly stable and precise. Think of it like a perfectly synchronized clock ticking millions or billions of times per second.
Stability is key there, I imagine.
Absolutely critical. Second, and this is where the information transfer happens, it must modulate these oscillations with the transmitted message. This is how your actual information, your voice, your data, your video is encoded onto that high-frequency carrier.
By changing it somehow.
Exactly. By cleverly altering its amplitude or its frequency or its phase.
Yeah.
And third, and critically, it needs to amplify the radio signal's power to ensure it reaches its intended destination over the required distance.
Right. Gotta have enough oomph.
Enough oomph to get there, whether that's across a room, across a city, or to a satellite in distant orbit. Without sufficient power, the signal would simply fade into the background noise.
So it's not just about creating the signal, but making it strong enough to overcome the vastness of space or the air and ensuring it arrives intact. What kind of other intricate components do we find inside a typical transmitter beyond that core generator and modulator? It sounds like quite a complex system already.
Oh, it is. Beyond those core units, modern transmitters are indeed quite complex integrated systems. They can include sophisticated video signal processing units to prepare the raw information, maybe compressing it or encoding it before modulation.
Okay, prepping the data.
Right. Then there are typically multiple power amplification cascades, essentially a series of increasingly powerful amplifiers that progressively boost the signal to the final desired output power.
Like steps on a ladder, getting stronger each time.
A good analogy. You might also find frequency multipliers and dividers to achieve specific operating frequencies from a base crystal oscillator, allowing for very precise frequency control.
Ah, for hitting the exact channel.
Precisely.
Yeah.
Power adders and dividers are used too, for instance, to combine the output of multiple amplifier stages for higher total power, or maybe to distribute power within something like an active phased array antenna system.
Okay.
And a crucial component, if modulation happens at an intermediate lower frequency before being shifted up to the final transmission frequency, would be up converters to perform that final spectral shift.
So potentially multiple frequency steps involved.
Potentially, yes. It's a highly integrated ballet of electronic components all working together.
That sounds like an incredible amount of interconnected parts, each performing its very specific, delicate job to prepare and then blast that signal out into the ether. When engineers design these complex systems, what are they really obsessing over? What are the key performance metrics or parameters they need to consider?
Right, what keeps them up at night? Engineers are indeed obsessed with a set of crucial design parameters that dictate a transmitter's performance and suitability for any given application. First, there's the operating frequency range, typically specified as FEM to FEMMAX. Pretty straightforward, defines the band it works in.
Okay, what channel can it use?
Exactly. Second, and this is paramount for reliable communication, is long-term relative frequency instability. This measures how much the frequency drifts from its precise nominal value under various destabilizing factors.
Like temperature changes.
Temperature changes, aging components, even power fluctuations. Keeping this drift absolutely minimal is vital, especially in regulated frequency bands where staying on your assigned channel is a legal and technical necessity. You can't just wander off.
Definitely not.
Okay, what else?
Third, the transmitter output power, PEEPer, indicates how strong the signal is when it leaves the antenna. Higher power generally means longer range or stronger reception, but also
More energy use and more heat, I bet.
exactly, more energy consumption and heat, and that leads right into the next one.
Which is efficiency, I assume. So crucial for power consumption and also preventing interference with other devices. Those must be massive considerations in our crowded airwaves.
Absolutely. Fourth, industrial efficiency is a critical metric. It's the ratio of the useful output power delivered to the antenna compared to the total DC power consumed from the supply. Engineers strive for this to be as high as possible.
Why is that so important? Well, to minimize energy waste, reduce operating costs, and manage heat generation, which can be a significant challenge in high-power transmitters. Fifth, the out-of-band emission coefficient K is vital. This measures any unwanted radiation that spills outside the intended operating band.
Leaky signals, basically.
Leaky signals, right?
Yeah.
It's usually expressed in decibels and represents the ratio of this unwanted power to the total transmitted power. This is incredibly important for preventing interference with other radio systems, ensuring electromagnetic compatibility, and adhering to strict regulatory standards.
Can't have your signal messing up someone else's.
Precisely. Finally, the modulation type and video signal parameters are crucial. This specifies what kind of information is being sent and precisely how it's encoded. This directly influences the design choices for the modulators and amplifiers within the transmitter.
Makes sense.
All these parameters are interdependent, requiring careful trade-offs and optimization during the design process. It's a real balancing act. 3. The receiver. Catching and unpacking the signal.
Okay, so the transmitter has done its complex job, blasting the signal out into the ether, maybe across continents or even to deep space. But by the time it reaches the receiver, that signal is often incredibly weak, right? Having dissipated its energy over vast distances.
Incredibly weak, often femtowatts or less.
And it's frequently buried deep within a sea of external and internal noise. What's the receiver's core mission in this incredibly challenging environment? How does it perform its magic?
Its main purpose is truly twofold, and it's a testament to engineering ingenuity. First, it has to meticulously extract that incredibly weak, useful signal from all that overwhelming interference, both external, like atmospheric disturbances, or signals from other radio stations.
And internal noise, too, from the receiver itself.
Critically, yes. Internally generated noise from the receiver's own components is often the bigger problem. It's truly like trying to find a whisper in the middle of a hurricane.
A whisper in a hurricane. Good analogy.
And second, after somehow isolating that signal, it must then precisely retrieve the valuable information, your voice, your data, your video, from that now recovered signal. And the key here is that to reliably extract any information, you absolutely need to achieve a minimum signal-to-noise ratio, or SNR, at the output of the receiver.
SNR, signal-to-noise ratio.
Right. Without sufficient SNR, the signal is simply indistinguishable from the noise, and your message is lost forever.
It sounds like a constant uphill battle against the invisible forces of randomness and interference. So how do we quantify how good a receiver is at this whisper-finding task? What are the key parameters for evaluating a receiver's performance?
The foundational source for our deep dive highlights several critical performance parameters for receivers. First, just like transmitters, there's the operating frequency range, FEMAX, which defines the specific band of radio frequencies it can tune into and process.
Okay, same as the transmitter range.
Generally needs to match, yes. Second, and perhaps one of the most critical for receivers, is the noise figure, N. This is a fundamental parameter that quantifies precisely how much additional noise the receiver itself adds to the incoming signal.
How much noise it makes internally.
Exactly. An ideal, perfectly noiseless receiver would have a noise figure of 1, or 0 dB when expressed in decibels, meaning it adds no noise. Any real receiver, however, adds its own noise, so its N is always greater than 1, or greater than 0 dB. The lower the N, the better.
So a lower noise figure truly means it's better at hearing those faint whispers even from across the globe. Better sensitivity.
Exactly. Which leads to the third parameter, sensitivity. This describes the receiver's ability to pick up very weak signals. Quantitatively, it's defined as the minimum input power or voltage required at the receiver's antenna to get a usable signal-to-noise ratio at the output.
That minimum SNR you mentioned.
Right, the minimum SNR needed for reliable information extraction. A more sensitive receiver can pick up signals from farther away or from lower power transmitters, extending communication range.
Makes sense. What else?
Fourth is selectivity. This is the receiver's crucial ability to pick out the desired signal from other strong, unwanted signals or interference present right there at the antenna, maybe on adjacent channels.
Ignoring the loud neighbors, basically.
Precisely. It's measured in decibels, comparing the power received at the desired frequency versus a nearby interfering frequency. High selectivity means your receiver isn't easily distracted or swamped by adjacent channels or powerful local broadcasts.
And what about handling signals of vastly different strengths simultaneously, like a super strong local radio station right next to a really faint signal from far away?
Yes. That's where dynamic range D comes in, the fifth key parameter. It's the ratio, expressed in decibels, between the maximum and minimum signal power the receiver can handle without significant distortion or loss of information.
So it can handle both loud and quiet signals at the same time.
Correct. A wide dynamic range means the receiver can simultaneously process both very strong local signals and very weak distant signals without being overloaded by the strong ones or losing the faint ones in the noise floor. It's a delicate balancing act.
Definitely sounds like it. Beyond these measurable parameters, what are the actual building blocks, the physical components that make up these functions inside a receiver?
Structurally, besides the obvious amplifiers that provide gain for sensitivity and the filters that ensure selectivity, receivers typically employ down converters. These are vital.
Down converters, why down?
They shift the high-frequency incoming signal from the antenna down to a lower fixed intermediate frequency, IF. This is a brilliant engineering trick, actually.
How so?
Because at that lower fixed IF, it's significantly easier and cheaper to amplify and filter the signal with very high performance. Components for lower frequencies are generally more stable, easier to design precisely, and less prone to unwanted parasitic effects.
Okay, so you convert everything to one standard internal frequency first.
Exactly. This principle, known as the super-heterodyne receiver architecture, is dominant in virtually all modern radio systems. It allows for incredibly precise tuning and strong performance. To achieve this frequency shift, you need local oscillators to generate the specific stable frequency that's mixed with the incoming signal.
The mixer signal.
Right. And finally, demodulators are responsible for extracting the original low-frequency video signal from the now down-converted radio signal. And decoders might be present to process any digital information embedded in the signal. So amplification, filtering, down-conversion, demodulation. That's the core flow. 4V. The fundamental distinction. Linear versus nonlinear elements.
Okay, you mentioned earlier, particularly with mixers, that crucial components rely on something called nonlinear elements. This sounds like a really fundamental concept that underpins much of what we're discussing. What's the core difference between linear and nonlinear elements in electronics, and why are both so incredibly important in transceivers?
Yes, this is truly where a lot of the fascinating signal processing magic happens. And it's a concept that sometimes sounds intimidating, but it's actually quite elegant when you break it down. Let's think about it this way.
Okay, lay it on me.
Linear elements are components like your standard resistors, capacitors, and inductors, provided their characteristics like the current voltage relationship for resistors or charge voltage for capacitors, are perfectly straight lines across all their operating ranges.
Straight lines. Got it.
The key defining characteristic of these is that their parameters resistance, capacitance, inductance do not depend on the amplitude of the oscillations passing through them. And crucially, this is a defining feature. They do not create new frequencies.
No new frequency.
None. If you put a single pure frequency in, you will get only that same frequency out. It might be weaker or stronger if it's an ideal linear amplifier or shifted in phase, but it's still the same frequency. They are essentially faithful processors, preserving the original spectral content without adding anything new.
So if I put a perfectly pure sine wave into a linear amplifier, I'll get a bigger but still perfectly pure sine wave at the exact same frequency out. No surprises, no extra musical notes appearing, so to speak.
Precisely. No extra notes.
Yeah.
Now, nonlinear elements are fundamentally different. These are typically semiconductor devices like diodes and transistors. Their characteristics are not straight lines, they are curves.
Curves, not lines, okay.
Their parameters do depend on the amplitude of the input oscillations and often on the specific DC bias, that's the constant voltage or current applied to them to set their operating point. And this is the critical aha moment for understanding transceivers. When signals pass through them, they generate new frequencies at their output that were absolutely not present at the input.
They create new frequencies. How?
It's inherent in their curved characteristic.
Yeah.
If you put a single frequency in, you might get its harmonics multiples of the original frequency. Or, and this is key for mixers, if you put in two frequencies, you'll specifically get their sum and difference frequencies out, among other things.
Whoa. So these new frequencies are the key. That's how you achieve complex operations like modulation and mixing then. My intuition might tell me these new frequencies are distortion, something bad, but here, it's actually harness.
You've hit on it exactly. That's the paradox that makes them so powerful. When signals are very small, nonlinear elements can behave almost linearly. In these cases, we use what are called differential parameters to analyze their small signal behavior around a fixed operating point.
Okay, for small signals.
But for larger signals, when they truly operate in their nonlinear region, which, as you said, is essential for their functionality in transceivers, we analyze them using methods like the quasi-linear method, which effectively averages parameters over the first harmonic of the input signal. It gets mathematically complex, but the principle holds.
Okay, so different ways to look at them depending on the signal size.
Right. And this distinction is crucial for understanding device function. Linear components are superb for faithful amplification, ensuring that your signal gets stronger without being distorted or having new unwanted frequencies appear. But nonlinear components are absolutely essential for a variety of tasks that form the backbone of radio communication.
Like what?
Like modulation, where you deliberately encode information by changing the carrier's amplitude, frequency, or phase. You need nonlinearity to impress that change, like frequency mixing conversion, which is used to precisely shift signals to different frequencies.
That down conversion to I you mentioned?
Exactly. Shifting from high RF down to a lower IF in a receiver, or shifting up from IF to RF in a transmitter. Also frequency multiplication, where you create higher stable frequencies from lower ones. And even signal generation itself, as oscillators inherently rely on nonlinearity to stabilize their amplitude, ensuring a continuous, stable output.
So without nonlinearity, we wouldn't have modulation, mixing, stable oscillators. Basically no modern radio.
Pretty much. The entire edifice of modern radio communication would collapse. It hinges on exploiting these nonlinear effects in very controlled ways.
So it's a careful and brilliant dance between harnessing the predictable, faithful reproduction of linear components and strategically exploiting the new frequency generating capabilities of nonlinear ones to perform complex signal manipulations. It's about using the right tool for the right job, even if one of those tools behaves in a way that seems messy or distorting from a purely linear perspective.
Exactly. It's like these seemingly imperfect components, the nonlinear ones, are the true alchemists of radio. They allow us to not just amplify signals, but to fundamentally transform them and even create entirely new ones needed for communication.
That's truly counterintuitive and brilliant. Okay, let's dig into those specific nonlinear components. The essential building blocks. Diodes and transistors. Let's get specific now. You just mentioned diodes and transistors as prime examples of these crucial nonlinear components. What are some of the key characteristics of these semiconductor devices that truly make all this incredibly sophisticated radio communication possible?
Okay, yes. Diodes and transistors are truly the fundamental building blocks of all modern radio frequency electronics, from the smallest wireless earbuds to the largest satellite dishes. Let's start with diodes, specifically the classic NP junction type.
The basic diode.
Right. These are the simplest semiconductor devices, characterized by a highly nonlinear current voltage IV relationship. It's that curve we talked about.
Okay.
The core concept of an NP diode is its one-way behavior. When forward biased, meaning a positive voltage is applied to the P-type region, current flows easily and exponentially. But when reverse biased, it essentially blocks current, acting almost like an open circuit.
The rectifier function.
Exactly, it's classic use. But there's more. Diodes inherently possess capacitance. There's diffusion capacitance when forward biased, which arises from the accumulation and movement of charge carriers, electrons, and holes within the semiconductor material.
Okay, capacitance when it's on.
And there's barrier capacitance when reverse biased, which is due to the depleted region that forms at the junction, acting like a tiny capacitor whose value changes with the reverse voltage.
So depending on how you bias it and the frequency of the signal, a diode isn't just a simple switch. It can also act like a variable capacitor. That sounds incredibly useful.
It is indeed. Diodes can be explicitly used as nonlinear resistors, which are essential for functions like mixers and detectors and radio systems, exploiting that curved IV characteristic. but they can also be exploited as voltage-controlled capacitors, known as varicaps or varictor diodes.
Varicaps. Variable capacitors.
Right. And those are crucial for tuning circuits electronically, like changing the channel in your radio, or for frequency multiplication, where you deliberately generate harmonics from a base frequency using that voltage-dependent capacitance.
Clever. Are there other important types of diodes?
Yes, definitely. We need to talk about Schottky diodes. These are a special, highly optimized type of diode with a metal semiconductor junction. Not a semiconductor NP junction.
Metal semiconductor, what's the difference?
Their key difference and critical advantage at high frequencies is that they create current using only majority carriers electrons in an N-type semiconductor, for instance. Not both electrons and holes like traditional NP diodes.
Only one type of carrier involved. Why does that matter?
It matters hugely because it means they effectively have no diffusion capacitance. Remember, diffusion capacitance comes from those slower-moving minority carriers accumulating. Without them, Schottky diodes are much, much faster.
Ah.
Exactly. This absence of diffusion capacitance means they can act as nonlinear resistors at much higher frequencies, extending well up into the hundreds of gigahertz range. This makes them absolutely vital components for microwave and millimeter wave applications, where NP diodes would be far too slow and inefficient due to that diffusion capacitance.
Got it. Schottky for speed at high frequencies. And then, of course, there are transistors, which truly feel like the workhorses of amplification and signal processing in almost any electronic device. How do they fit into this high-frequency world?
Absolutely. Transistors are the active elements that provide amplification and enable oscillation, essentially acting as incredibly precise controlled switches or current voltage amplifiers. Let's talk about bipolar junction transistors, BJT, first.
BJTs.
Okay. For high-frequency applications, NPN transistors are generally preferred over PNP. Why? Because their operation relies primarily on the movement of electrons, and electrons simply have inherently higher mobility. They move faster than holes in all common semiconductors.
Faster electrons mean faster transistors.
Precisely. This higher mobility means electrons can cross the crucial base region faster, significantly reducing what engineers call transit time and allowing for much higher operating frequencies.
And they amplify, right? How does that work again?
Their active properties are quite remarkable. A transistor functions by converting DC power from its power supply into the AC power of the oscillating or amplified signal. It's a true energy converter, not just a passive conduit.
Takes DC, makes RF AC?
In essence, yes. For amplification, the emitter-base junction is forward biased, allowing a small current to flow into the base, and the collector-base junction is reverse biased to collect those carriers that make it across the base. A small signal applied at the input, the base, then precisely controls a much larger current at the output, the collector. That's how amplification is achieved.
So they're not just passively passing signals, they're actively adding energy to them, growing the signal from a small input. What about their operating characteristics? How do engineers think about their fundamental behavior?
We describe their fundamental behavior using static characteristics, which are essentially graphs showing the relationship between currents and voltages under steady DC conditions. These define three key operating regions. The active region, where the transistor amplifies linearly and is most commonly used for amplification.
The main amplification zone.
Right. Then the saturation region, where both junctions are forward biased and the transistor acts like a fully closed switch, allowing maximum current to flow. And finally, the cutoff region, where both junctions are reverse biased and virtually no current flows, acting like an open switch.
Active, saturated, cutoff. Got it.
Transceivers primarily utilize the active region for amplification, and sometimes the cutoff and saturation regions for efficient switching, or in certain amplifier classes we'll discuss later.
Okay. You mentioned transit time. Is that the main limit on how high a frequency a BJT can handle?
It's a huge factor. An incredibly important consideration for high-frequency operation is what we call inertia, or frequency limits. As frequencies increase, that transit time of electrons across the base becomes significant, eventually approaching the period of the signal itself.
The electron can't keep up with the signal oscillation.
Essentially, yes. This causes noticeable phase shifts between the input and output currents, which effectively limits the transistor's gain at higher frequencies. The transit frequency, FT, is a key metric for any transistor. It's the theoretical frequency at which the current gain of the transistor drops to unity, or 0 dB.
Gain becomes 1, so it stops amplifying.
Right. It indicates its maximum useful operating frequency, Beyond P, its ability to amplify diminishes rapidly.
Okay. And then there are field effect transistors, or FETs.
Mm.
How do they differ from BJTs, and why are they also so important in high-frequency design?
Right, field effect transistors, FETs, operate on a fundamentally different principle from BJTs. Instead of controlling current flow by injecting carriers into a junction, like base current and BJT, current flow in FETs is controlled by an electric field, which modulates the width of a conductive channel through which carriers flow.
Controlled by a field, not a current. Interesting.
Yes, and this gives them very high input impedance, which is a major advantage in many applications, especially where you don't want the amplifier to load down the input signal source.
What types of FETs are common at high frequencies?
Among FETs, Schottky barrier FETs, MESFETs, using that fast Schottky junction for the gate, are used extensively up to several tens of gigahertz. They utilize a Schottky barrier for the gate, which is typically reverse biased. The current in the channel is precisely controlled by the voltage applied to this gate.
Okay, MESFETs up to tens of gigahertz. What about even higher, millimeter waves?
For even higher frequencies, pushing into the millimeter wave range, say above 30 gigahertz, we turn to the HEMT, high electron mobility transistor.
HEMT. This is where we really get into some advanced materials science and truly ingenious design, right? What's the aha moment with HEMMs? What makes them so special for these extreme frequencies?
You got it. The core idea here is to achieve absolutely incredibly high electron mobility, meaning electrons can move through the material with minimal resistance and scattering, much faster than in conventional materials.
How do they do that?
It's done by using a heterojunction, a carefully engineered junction between two different semiconductor materials, like aluminum gallium arsenide, AlGaAs, and gallium arsenide, GAs. Through clever doping and precise material layering, electrons are effectively pushed into an undoped GAs layer.
Undoped. Pure.
Extremely pure GAs, which has virtually no impurities to scatter them. This allows the electrons to move much, much faster. The source quotes mobilities up to 10,000 centimeters squared V compared to maybe 8,000 in standard MESFETs. It's like giving them a dedicated frictionless superhighway compared to a bumpy, crowded road.
Wow, a significant jump in speed.
It is. And that speed directly translates to significantly higher frequency operation, pushing the boundaries of what's physically possible for transistors well into the millimeter wave spectrum.
Amazing. Are there other advanced types?
Yes, we should also mention HBTs, heterojunction bipolar transistors. These ingeniously combine the advantages of heterojunctions using different materials with the traditional bipolar transistor structure.
Best of both worlds.
Kind of. They're specifically designed for very high power at high frequencies. They often feature a vertical structure that facilitates much better heat dissipation, allowing them to handle significantly more power than many FETs at similar frequencies. They are crucial for high-power, high-frequency transmitters, like in radar or base stations.
It's truly incredible how material science and clever device design can constantly push these limits, constantly battling the inherent physics to achieve higher and higher performance, leading to faster, more robust wireless communication.
Boosting the signal.
So we have our signals being generated and modulated, and we understand the fundamental transistors like BJTs, FETs, HEMTs that can amplify them. But what really goes into designing a power amplifier, especially for those high frequencies, say, above 1 gigahertz? It can't just be the transistor sitting there by itself, can it?
No, you're absolutely right. While the transistor is indeed the beating heart of any amplifier, a power amplifier, especially one using a BJT in a common emitter configuration, needs several key supporting circuits to function effectively and efficiently. It's a whole system.
What kind of supporting circuits?
First, there's a meticulously designed input matching network. This is absolutely crucial to ensure maximum power transfer from the signal source, like an earlier amplifier stage or a modulator, to the transistor's input.
Matching again. Why is that so critical at the input?
If the impedances aren't perfectly matched, a significant portion of the input power will simply reflect back, reducing the overall efficiency and gain. You want all that precious input signal to actually get into the transistor to be amplified.
Makes sense. What else?
Second, an output resonator, often a precisely tuned LC circuit, inductor capacitor, in a collector circuit, is essential. This network is tuned to the specific operating frequency. It serves two main purposes. It filters out unwanted harmonics generated by the transistor.
Cleaning up the signal.
Right. And it also acts as an output matching network, efficiently transferring maximum power from the transistor to the load, which might be an antenna or the next stage in the system. Again, minimizing reflections.
Okay, matching on both input and output. What else is needed?
Third, stable bias circuitry is non-negotiable. This provides the necessary stable DC voltages and currents for the transistor to operate correctly at its specific operating point, the bias point ensuring it's in the active region or the desired class of operation we'll talk about. An unstable bias means unstable performance, gain fluctuations, distortion. Just bad news.
Rock solid DC power. Got it.
And finally, decoupling blocking elements, typically cleverly placed capacitors and inductors, are used to separate the AC signal paths from the DC power paths. This prevents signal energy from leaking into the power supply or DC voltage, from disrupting the delicate RF signal path. Keeps everything clean and separate.
So input matching, output resonator matching, bias, and decoupling. Quite a bit around the core transistor. And when you're designing these complex circuits, the ultimate goals are high output power, maximum gain, and excellent efficiency, right? Those seem to be the universal metrics for any amplifier.
Yes, those are indeed the primary figures of merit that engineers strive to optimize. Output power, POUT, is simply the amplified power delivered to the load. Power gain, KP, is the ratio of output power to input power, POUT pin, clearly indicating how much the signal is magnified.
Pretty straightforward.
And efficiency, which is the ratio of the useful output AC power to the total DC power consumed, POUT PDC, tells you how much of the supplied DC power is actually converted into useful RF output power, the rest.
Lost is heat. Lost is heat. Exactly. For high-power applications, efficiency is absolutely paramount, not just for power savings, but also for managing the significant heat generated. That heat can damage components if not properly handled with heat sinks and cooling systems.
Okay, that makes sense. Now, I've often heard about different classes of amplifiers, like Class A, B, and C. What's the deal with those? They sound like distinct modes of operation with very different trade-offs.
They are exactly the different operating modes for the transistor, specifically defining for how much of the input signal cycle the transistor is on and conducting current. And yes, this fundamentally impacts the amplifier's performance trade-offs, particularly the classic battle between linearity and efficiency.
Linearity versus efficiency, the big trade-off. Tell me about Class A.
Okay, linear mode. Class A. In this mode, the transistor conducts current throughout the entire 360-degree input signal cycle. Our source describes this using a cutoff angle of 180 degrees, meaning it's effectively always on, biased right in the middle of its linear region.
Always on. What are the pros and cons? The huge pro here is excellent linearity. Because it's always on and operating in that straight line part of its characteristic, it means virtually no new unwanted frequencies are added. This makes it ideal for amplifying complex signals like amplitude-modulated voice or video, where preserving the original waveform without distortion is absolutely critical.
So, very clean amplification. What's the downside?
The significant con is its inherently low theoretical maximum efficiency, which is only 50%. In practice, it's often much lower. A considerable amount of power is always dissipated as heat, even when there's no input signal, because the transistor is continuously conducting that bias current.
So Class A is the purest, cleanest mode, but it's also quite wasteful in terms of energy and generates a lot of heat. What about the other classes? How do they achieve better efficiency?
Right. To get better efficiency, you move to modes with collector current cutoff, which include Class B, Class AB, and Class C. In these modes, the transistor is deliberately biased, so it conducts current for only a portion of the input signal cycle. The cutoff angle is less than 180 degrees.
So it switches off for part of the cycle.
Exactly. For example, an ideal Class B is 90 degrees, meaning it conducts for exactly half the cycle. For Class C, it's even less than 90 degrees, meaning the transistor is off for a significant majority of the cycle, only turning on for brief pulses near the peak of the input signal.
Why do that? What's the benefit?
The core concept is that by allowing the transistor to switch off for part of the cycle, you significantly reduce the average DC power dissipated by the transistor itself. The pros are dramatically higher efficiency. The theoretical maximum can approach 100% as it gets very small, approaching Class C. This means much less heat is dissipated, making them perfect for high-power applications where heat is a major concern.
Higher efficiency, less heat. Sounds great. What's the catch?
The catch is significant. These modes are inherently nonlinear, because the transistor is essentially switching on and off, chopping up the signal waveform. This means they inevitably generate strong harmonics, multiples of the input frequency, and potentially intermodulation products, new unwanted frequencies created when multiple input signals interact at the output.
Ah, so they create distortion, those unwanted frequencies again.
They do. And this is precisely why a highly selective output resonator or filter is absolutely crucial in these designs. Its job is to aggressively filter out all these unwanted harmonics and distortion products, leaving only the desired amplified signal at the fundamental frequency.
So you gain efficiency, often dramatically, but you inherently lose linearity and need a good filter to clean up the mess.
That's the fundamental trade-off exactly. Engineers must carefully balance these characteristics for this specific application. For instance, Class C is often used for constant envelope signals like FM radio or CW Morse code, where amplitude linearity isn't critical and you just want maximum power efficiency.
So if I want maximum efficiency for, say, a continuous wave signal that doesn't carry complex amplitude information, I might choose Class C. But if I want a crystal clear, undistorted voice or video signal, I'd probably stick closer to Class A, or maybe Class AB, which is a compromise between A and B, even if it costs me more power and generates more heat.
You've got it perfectly. It's a fundamental design decision based on the signal type and system requirements. And the source also dives into the importance of selecting the optimal load resistance, RK, for the transistor. This isn't arbitrary, it's carefully chosen.
Optimal load, why?
It's chosen to allow the transistor to swing its output voltage and current over the widest possible range for maximum power or efficiency, without driving it into unwanted saturation, fully on, or cut off, fully off, too hard, or exceeding its voltage or current limits, which could cause distortion or even damage. It's often quantified by something called the tension coefficient, which relates the output voltage swing to the supply voltage, ensuring the transistor operates in its absolute sweet spot for power delivery.
Finding that perfect sweet spot. And then there's the concept of matching the impedances. We hear this term thrown around a lot in electronics. Why is impedance matching so critically important throughout the entire signal path in a radio system?
Impedance matching is absolutely crucial throughout the signal chain because it directly impacts how efficiently power is transferred from one stage to the next or to the antenna.
Maximum power transfer.
That's the goal. The core concept is simple physics. Maximum power is transferred between a source and a load when their impedances are conjugate matches. For purely resistive circuits, this simply means their resistances are equal.
Okay, match the resistance.
In practical terms, modern RF devices are typically designed to work with standard impedances, most commonly 50 ohms. That's the characteristic impedance of many transmission lines like coaxial cables and circuit board traces. However, transistors themselves have complex input and output impedances. They look like a resistance and a capacitance or inductance, and these values vary significantly with frequency.
So the transistor doesn't naturally look like 50 ohms.
Rarely. So the purpose of those matching circuits we talked about, typically intricate LC networks like G-shaped circuits or more complex arrangements, is to transform the transistor's complex impedance to that standard 50 ohms or whatever the system impedance is.
Like an electrical transformer, but for impedance?
Kind of, yes. It ensures efficient power transfer from the source to the transistor and from the transistor to the load, while also minimizing signal reflection. Reflections cause standing waves, waste power, and can degrade performance or even damage components. These matching circuits often have filtering properties as well, contributing to overall signal integrity.
So matching is key for power, efficiency, and signal quality. What are some of the particular challenges when we push into those really high frequencies, the microwave range, say, above 1 gigahertz? It sounds like components start behaving in unexpected ways then.
Oh, yes. At microwave frequencies, entirely new and profound challenges emerge because parasitic effects become dominant. These aren't design components. They're unintended inductances, capacitances, or resistances arising from the physical layout, the component packaging, even the tiny internal bond wires within a transistor chip itself.
Stray effects that you didn't intend.
Exactly. For example, the source highlights that even the tiny inductance of a transistor's internal emitter lead in a common emitter bipolar transistor can drastically reduce power gain at microwave frequencies.
Just a tiny bit of wire inductance.
Yes. The source indicates that gain can drop sharply, potentially approaching unity, no gain, at frequencies above just 1 gigahertz for standard BJTs in this configuration. This happens because a portion of the input power gets effectively bypassed or shunted through this parasitic inductance rather than going through the active part of the transistor where amplification happens. It essentially short-circuits your signal path at high frequencies.
Wow. So standard transistors just stop working well.
Their performance degrades rapidly. This severe limitation is precisely what drives the shift to new materials and specialized device structures for microwave and millimeter wave work. For instance, gallium arsenide, GAs, and those specialized HEMTs and HPTs we discussed earlier are crucial. These materials inherently have better high-frequency properties, like higher electron mobility, and the device structures are meticulously designed to minimize these parasitic effects. They're engineered specifically to overcome these high-frequency limitations.
So the materials and structures themselves are optimized for microwaves.
Absolutely. Furthermore, at these very high frequencies, S-band, around 2 to 4 gigahertz, and above, for example, traditional lumped element, LC matching circuits, like those G-shaped networks, become difficult or impossible to implement physically. Why? Because their physical dimensions start becoming comparable to the signal wavelength itself. A tiny capacitor might start looking like an inductor.
So the components don't behave like simple L's and C's anymore.
Exactly. Instead, engineers use sections of transmission lines themselves, precisely dimensioned traces on a circuit board, or waveguides designed to act as the matching networks. Examples include quarter-wave transformers or single-stub tuners. These carefully designed geometric structures precisely compensate for complex impedances and ensure signal integrity using distributed effects rather than lumped components. It's a fundamental paradigm shift in high-frequency circuit design.
It's truly a constant battle against physical limitations, forcing engineers to get incredibly creative with materials, structures, and even the very geometry of their circuits to achieve higher and higher performance, pushing the boundaries of what's possible for wireless communication.
The unwanted companion.
Okay, this is fascinating. You mentioned earlier, especially with receivers, that they are constantly battling noise. What exactly is this noise, and why is it such a pervasive and fundamental problem in every communication system? It sounds like it's the ultimate villain in this story.
It really is the ultimate adversary in many ways. Noise is essentially unwanted, random electrical fluctuations that corrupt or obscure the useful signal you're trying to detect or process. It's inherent in any electronic system, and indeed in the natural physical world around us.
It's just there. Unavoidable.
Fundamentally, yes, at least some types are. In receivers, especially at microwave frequencies where signals are often incredibly weak to begin with, internal noise generated within the receiver's own components is often the primary culprit. It frequently far outweighs external interference from the environment or other radio signals. It's the unavoidable background static, the electronic hiss, that makes faint signals even harder to detect and differentiate from randomness.
So even a simple resistor, just a piece of wire practically, can be noisy. That's quite surprising to think about.
Absolutely. The most fundamental type of noise present in any resistive element is thermal noise, also known as Johnson-Nyquist noise.
Thermal noise, related to heat.
Directly. The concept is that any resistor at a temperature above absolute zero, T0 Kelvin, will have its electrons moving randomly and chaotically simply due to their thermal energy. Think of it like a microscopic mosh pit within the material constantly bumping around.
Okay, electrons jiggling around because of heat.
Exactly. This chaotic movement creates a constantly fluctuating random voltage across the resistor's terminals. The mean square of this noise voltage is directly proportional to the absolute temperature, P, the resistance R of the component, and the bandwidth over which you're measuring it. The famous formula is 4kTr, where K is Boltzmann's constant.
Okay, so hotter resistors are noisier, higher resistance is noisier, wider bandwidth picks up more noise.
Precisely. It's often called white noise because its spectral power density, the noise power per unit of frequency, is constant across a very wide range of frequencies, much like white light contains all colors of the visible spectrum. Interestingly, the source notes that ideal capacitors and inductors themselves don't generate thermal noise, only resistive elements do. Real ones have some resistance, of course.
So the primary source is resistance and heat. Are there other types of noise that are important to consider, especially in active devices like transistors, beyond just the heat-related kind?
Yes, particularly in transistors and other active semiconductor devices. Another significant type is flicker noise, often called 1F noise.
1 over F. Why that name?
Because its spectral power density decreases inversely proportional to frequency. It goes as 1F. This means it's most prominent at very low frequencies, down near DC, and becomes less significant as you go higher up in the spectrum, where thermal noise usually dominates.
So it's mainly a low-frequency problem?
Predominantly, yes. Its origin is complex and not always fully understood, often associated with various processes like charge carriers getting trapped and released in semiconductor materials, surface effects, or defects in the crystal lattice. These cause slow, random fluctuations in current or voltage. While thermal noise is flat across frequency, white, flicker noise dominates at the lower end of the spectrum and needs careful management in low-frequency circuits or the baseband sections of transceivers.
Okay, thermal noise and flicker noise. Given all this unavoidable noise, how do engineers quantify how noisy a receiver is, or a specific component like an amplifier? It sounds like you need a really precise, standardized way to measure its noisiness.
Absolutely. We use a critical parameter called the noise figure, N, sometimes denoted F. Its definition is the ratio of the signal-to-noise ratio, SNR, at the input of a device to the SNR at its output.
Input SNR divided by output SNR. Wait, shouldn't it be the other way around if it's adding noise?
Good question. Think of it this way. SNR ideally stays the same or improves if gain is involved relative to noise. But a real device adds noise, making the output SNR worse, smaller than the input SNR.
Yeah.
So noise figure, input SNR, output SNR, is always greater than or equal to 1.
Ah, okay, so a higher N means the device degrades the SNR more, meaning it's noisier.
Exactly. An ideal, perfectly noiseless amplifier would add no extra noise, so the output SNR would equal the input SNR, assuming unity gain for simplicity, and N would be 1. In decibels, that's 0 dB. Any real amplifier adds its own internal noise, degrading the SNR, so N is always greater than 1, or 0 dB. The lower the N, the better the component or receiver is at preserving the original signal quality against the internal noise it generates.
Makes sense. Lower N is better. You mentioned noise temperature, too.
Yes, for very low noise devices, where N is very close to 1, like maybe 1.1 or 1.2, calculating N directly can be tricky and less intuitive. So especially in fields like radio astronomy or satellite communication, we often use noise temperature, SHUM, instead. This is calculated as SHUM N1 PDC, where T0 was a standard reference temperature, usually 290 Kelvin, about room temperature.
So it represents the extra temperature the device seems to add due to its internal noise.
Precisely. It gives a more intuitive physical feel. This amplifier behaves as if it has an extra 50 Kelvin of thermal noise at its input, for example. A lower noise temperature means lower added noise, just like a lower noise figure. It's particularly useful when dealing with cascaded systems.
Okay, that leads to my next question. This is really important. If every single component adds noise and it seems physically unavoidable, how do you design a really, really sensitive receiver that can pick up those incredibly weak signals from far, far away? It almost sounds like a losing battle against ever-increasing noise.
It does seem like that, but there's a crucial insight that makes sensitive receivers possible. This comes from the Freeze formula for noise figure in cascaded systems, though our source gives an expanded version covering noise temperature too.
The Freeze formula, what's the key insight?
The absolutely key insight from this formula is that the overall noise figure, or noise temperature, of a cascaded system, like a receiver with multiple amplifier stages connected one after another, is primarily overwhelmingly dominated by the noise figure and gain of the very first stage in the chain.
The first stage, why is that one so important?
Because any noise added by that very first amplifier gets amplified by all the subsequent stages, along with the original signal. Noise added later in the chain gets amplified less. So the noise contribution of that first stage has the biggest impact on the final output SNR.
Ah, okay. So you need to make that first stage incredibly low noise and ideally have high gain.
Exactly. That's precisely why the very first amplifier directly after the antenna in any sensitive receiver is almost universally a low-noise amplifier, LNA. Transistors for LNAs are specifically selected, often using those advanced HEMT devices we discussed, and rigorously optimized for the absolute minimal noise figure and maximum stable gain achievable at the operating frequency.
So the LNA's job is to boost the weak signal before it gets swamped by noise from later stages.
You've got it. The entire goal is to amplify that tiny, precious incoming signal as much as possible while adding the absolute minimum amount of extra noise itself before that signal gets drowned out by the inevitable, usually higher noise contributions from subsequent components like mixers, filters, and further amplifier stages. Sometimes, if the antenna picks up very strong, unwanted signal interferers that could potentially overload the sensitive LNA, a filter called a pre-selector might be strategically placed before the LNA to block those strong signals and protect the LNA, ensuring its optimal low-noise operation on the desired weak signal. Controlling that first stage's noise is absolutely critically important for overall receiver sensitivity. It sets the noise floor for the entire system. 8. Oscillators and synthesizers. The heartbeat of radio.
Okay, let's shift gears slightly. Every radio signal needs a rock-steady heartbeat, right? A stable, precise frequency to ride on, whether that's the carrier wave in a transmitter that defines the channel, or the local oscillator in a receiver that's used to mix the incoming signal down to the intermediate frequency.
Hmm.
This is where oscillators come in. What exactly is an autogenerator, as the source calls it, and what are the main demands placed upon them for reliable communication?
Right, the heartbeat is a great analogy. An autogenerator, or more commonly just a self-excited oscillator, is a remarkably clever device. Its purpose is to produce continuous electromagnetic oscillations entirely on its own, given only a DC power supply. Unlike a signal generator that needs an external input signal to start, it self-starts and maintains its own rhythm.
It just starts oscillating.
Under the right conditions, yes. The primary demands on an autogenerator in radio systems are twofold and extremely stringent. First, as you said, extreme frequency stability. It needs to stay precisely on its assigned channel or frequency without drifting, even slightly, over time, temperature changes, or variations in load. Second, especially for modern digital systems, it needs a very low level of phase noise.
Phase noise again, we'll come back to that. So stability and low phase noise are key. What are the essential ingredients of an autogenerator? What makes it tick autonomously and generate that stable frequency?
The source identifies 4 critical parts working together in a continuous feedback loop. You need all 4 for it to work reliably. First, you need a resonator. This is the frequency-determining element.
The tuning fork, basically.
Exactly. It sets the desired frequency and provides the memory or timing reference for the oscillations. Think of it like a precisely tuned pendulum in a grandfather clock, or a quartz crystal, which is very common, or maybe an LC tank circuit. It has a Q factor, or quality factor, which indicates how cleanly and persistently it rings at its natural frequency. A higher Q means a more stable, sharper resonance, less prone to being pulled off frequency by external influences.
Okay, resonator sets the frequency. What else?
Second, an active element, usually a transistor like a BJT or FET, is absolutely essential. This component does the work. It takes energy from the DC power supply and actively converts it into AC energy, precisely timed by the resonator, to replenish the tiny energy losses that inevitably occur in the resonator and the rest of the circuit due to resistance.
So it overcomes the losses to keep it going.
Precisely. It provides the gain needed to sustain the oscillation. Third, a feedback loop is critical. A portion of the energy from the resonator's output, or the active element's output, is deliberately fed back to the input of the active element. Crucially, this feedback must arrive in precisely the correct phase to reinforce the oscillations already happening. This is the synchronization mechanism that keeps the system locked onto the resonator's frequency.
Positive feedback in the right phase.
Exactly. And fourth, and this is often overlooked but vital for stable operation, is a nonlinear element. This is crucial for amplitude limiting. When the oscillator starts up, the loop gain is usually slightly greater than 1, causing the oscillations to build up in amplitude. As they grow, the active element, typically the transistor itself as its operating point shifts, enters a nonlinear operating region. This nonlinearity naturally reduces the effective gain of the loop until it becomes exactly 1, thereby limiting the amplitude to a stable, constant value.
The nonlinearity prevents it from growing forever or distorting wildly.
Correct. Without this inherent nonlinearity providing amplitude stabilization, the oscillations would either die out immediately or grow uncontrollably until limited by the power supply rails or potentially destroying the circuit.
So it's a wonderfully self-sustaining system, almost like a miniature, perfectly balanced ecosystem. Resonator for frequency, active element for energy, feedback for synchronization, and nonlinearity for stability. How does it know what frequency to oscillate at, and how does it become so stable and precise? What are the underlying conditions?
It relies on 2 fundamental conditions being met simultaneously, often called the Barkhausen criteria for oscillation. First is phase balance. The total phase shift around the entire closed loop, that's the resonator, the active element, the feedback path, all of it must be an integer multiple of 360 degrees, or 0, 2, 4 radians, etc. This ensures that the feedback signal arrives back at the input exactly in phase, constructively interfering to reinforce the original signal and keep the oscillation alive.
Phase has to line up perfectly.
Perfectly. Second is amplitude balance. The total magnitude of the gain around the entire loop must be exactly equal to 1 at the oscillation frequency. If the loop gain were greater than 1, the amplitude would grow exponentially. If it were less than 1, any oscillation would die out. As we just discussed, the nonlinearity in the active element is what automatically adjusts the gain to exactly 1 once oscillations have started, stabilizing the amplitude.
Gain equals 1, phase equals 0, or 360, got it. And stability comes mainly from the resonator.
Yes, the resonator's Q factor is absolutely paramount for frequency stability. A high Q resonator has a very sharp phase response near its resonant frequency. This means even small, unavoidable phase shifts caused by temperature changes or voltage fluctuations in the other components, the transistor, the feedback network, will only cause a very tiny shift in the overall oscillation frequency needed to bring the total loop phase back to zero. The high Q resonator strongly pulls the oscillation frequency towards its own stable natural resonant frequency. Weak coupling to the load also helps maintain this high Q, isolating the resonator from external influences.
But what if you need to change the frequency, like tuning a radio or changing channels on a Wi-Fi router? A simple auto generator, by its very nature with that fixed resonator, seems stuck at one frequency. How do you get a radio that's both tunable across many channels and incredibly stable?
Excellent question. That's precisely where frequency synthesizers come in, and they are one of the most remarkable and ubiquitous innovations in modern radio. Their purpose is to allow the output frequency to be changed, often digitally, in precise, discrete steps over a potentially very wide range, while still maintaining extremely high frequency stability.
Flexibility and stability, how do they manage that?
They typically achieve this stability by referencing a very stable low-frequency quartz crystal oscillator, maybe running at 10 or 20 megahertz, which acts as the ultimate master clock or frequency standard for the entire system. Quartz crystals have incredibly high Q factors and excellent temperature stability.
Okay, so they use a stable crystal as a reference. What's the core technology?
The core technology, detailed in our source and used almost universally, is the phase-locked loop, PLL. A PLO is an ingenious feedback control system that essentially locks the frequency and phase of a less stable but electronically tunable oscillator, called a voltage-controlled oscillator, VCO, to that highly stable reference frequency from the crystal oscillator.
Phase-locked loop.
Yeah.
Locking the VCO to the reference. How does it work, basically?
Here's a simplified breakdown. The VCO's output, which is the desired tunable high frequency, maybe gigahertz, is fed into a programmable frequency divider. This digitally divides the VCO's frequency down by a variable factor. Let's call it N.
Okay, divide the fast signal down.
Right. This divided down VCO signal is then fed into one input of a phase frequency detector, PFD. The PFD's other input receives a signal derived from that highly stable crystal reference oscillator, perhaps also divided down by a fixed factor R. The PFD constantly compares the frequency and phase of these two signals, the divided VCO and the divided reference.
It compares them. What happens then?
If their frequencies or phases don't match perfectly, the PFD generates an error signal, a voltage proportional to the difference. This error signal is then filtered by a low-pass filter called the loop filter, which is crucial for stability and noise performance. And the resulting smooth DC voltage is used to control the VCO.
Ah, the error signal adjusts the VCO's frequency.
Exactly. It continuously adjusts the VCO's frequency, pulling it higher or lower until its divided down frequency precisely matches the divided down reference frequency, and their phases are locked together. The loop settles with zero frequency error and a constant phase offset.
So by simply changing that N factor in the programmable divider, maybe just by sending a digital command to it, you can dial in a different output frequency from the VCO anywhere within its tuning range, all without sacrificing the rock-solid stability inherited from the crystal reference. That's an incredibly elegant and clever solution.
It is indeed a backbone of modern frequency agile radios. The output frequency of the VCO becomes a precise multiple NR times of the stable crystal reference frequency, allowing for flexible, stable, digitally controlled tuning across a wide range. It's the reason your smartphone can jump seamlessly between dozens of Wi-Fi channels or cellular bands while maintaining perfect communication.
So you get this amazing combination of flexibility and stability, which is fantastic. But are there any new challenges or downsides that synthesizers, particularly PLLs, introduce? Nothing in engineering is ever truly perfect, is it?
You're absolutely right. There are always trade-offs and new challenges. The main one, and a very critical parameter in modern high-speed digital communications, is phase noise. We mentioned it earlier with oscillators, but it's a particular concern in PLLs.
Phase noise again. Remind me what it is.
Phase noise refers to tiny, random, rapid fluctuations in the phase, and consequently, the instantaneous frequency of the oscillator's output signal. Instead of being a perfectly pure tone at a single frequency, the output signal has these slight random jitters in its timing. In the frequency spectrum, it doesn't appear as a perfectly sharp line, but rather as skirts or side bands of noise spreading out from around the main desired carrier frequency. It makes the signal slightly blurry or fuzzy in the frequency domain.
And why is that fuzziness a problem?
The impact of phase noise is significant. In modern communication systems, where information is often encoded not just in amplitude, but also very precisely in the phase or frequency of the signal, like in digital modulation schemes such as QAM or OFDM used in Wi-Fi and 5G, phase noise directly degrades signal quality. It can cause errors in data reception, increase the bit error rate, limit the data throughput, and critically, it limits how closely channels can be spaced in a crowded spectrum without interfering with each other. Those noisy skirts can spill into adjacent channels.
Okay, so phase noise messes up the data and causes interference. What causes it in a PLL?
The noise comes from multiple sources within the loop. The VCO itself inherently has phase noise. The reference crystal oscillator has some phase noise, though usually very low. Even the phase frequency detector and the charge pump that often follows it contribute noise. And fundamentally, transistor noise, thermal and flicker noise within all these components is a primary source of these random fluctuations that get converted into phase fluctuations.
So noise is everywhere in the loop.
Pretty much. And the challenge for engineers is that there's a fundamental trade-off in PLL design related to phase noise. To reduce the phase noise contributed by the VCO, which is often the dominant source close to the carrier, you generally want the PLL loop bandwidth to be wide. But to reduce noise coming from the reference, or PFD, which often dominates further away from the carrier, you want the loop bandwidth to be narrow.
Conflicting requirements.
Exactly.
And there's another trade-off mentioned in the source. To reduce the overall noise multiplication effect, noise increases with the square of the division ratio n, you generally want to increase the frequency of the reference oscillator that the PFD compares against. This lowers n for a given output frequency. However, higher frequency crystal oscillators or reference sources often have worse long-term stability or higher phase noise themselves further from the carrier. So engineers are always searching for that optimal reference frequency and loop bandwidth that balances low phase noise across the relevant frequency offsets with good long-term stability, fast locking time, and reasonable power consumption. It's a complex, multi-dimensional optimization problem that continues to push the limits of synthesizer design.
It sounds like a constant, intricate optimization problem balancing absolute stability, wide-ranging flexibility, and the unavoidable presence of noise from multiple sources to get the best possible, cleanest signal for our incredibly demanding modern communication systems. Next, frequency converters. Shifting the spectrum. We've talked about transmitters creating high-frequency signals and receivers needing to pick them up, often incredibly weak. And we just talked about oscillators generating stable frequencies. But there's another crucial component that helps signals move between different parts of the spectrum within both transmitters and receivers. What are frequency converters, often called mixers, and why are they so profoundly important to how radio systems function?
Yes, frequency converters and specifically mixers are absolutely essential workhorses. Their job is to shift the frequency of a radio signal either up or down in the spectrum in a controlled way. They are the unsung heroes that enable signals to be generated, processed, and detected efficiently at different stages in a complex radio system. Without them, most modern radio architectures, especially the superheterodyne receiver, simply wouldn't be possible or practical.
Okay, so shifting frequencies. How are they used in transmitters and receivers?
In a transmitter, they often act as up-converters. They take a lower frequency signal that has already been modulated with the information maybe at an intermediate frequency, IF, where modulation is easier to do cleanly, and then they mix it with a higher local oscillator frequency to move its entire spectrum up to the final, much higher carrier frequency required for transmission into the air.
So modulate low, then mix high for transmission.
Often, yes. Conversely, and perhaps even more critically, in a receiver, they function as down-converters. They take the very high-frequency incoming signal directly from the antenna, after the LNA usually, and mix it with the local oscillator signal to shift it down to a fixed, much lower intermediate frequency, IF.
That super heterodyne principle again. Why is that IF step so useful?
It's a brilliant engineering strategy. Instead of having to build amplifiers and filters that can handle wildly varying, extremely high radio frequencies directly throughout the receiver, which is very difficult and expensive, we down-convert the desired channel, whatever its frequency, to a single much lower, fixed intermediate frequency. Think of it like a universal translator inside the receiver, no matter what high-frequency radio channel comes in, say 900 millihertz or 2.4 gigahertz or 5 gigahertz. It's first converted into a common, easy-to-process internal language, maybe 70 millihertz or 10.7 meters.
Okay, processing happens at that fixed lower IF.
Exactly. This makes building incredibly precise, high-performance, and stable filters and amplifiers for that single IF frequency much, much simpler, more cost-effective, and higher performing than trying to do it directly at RF. It's the key to selectivity and sensitivity in most radios.
How do they work their frequency shifting magic? What's actually happening inside a mixer to achieve this fundamental transformation of a signal's frequency? It involves that nonlinearity again, right?
Precisely. The core idea is based on the mathematical multiplication of two input signals using a nonlinear element. Remember, we discussed how nonlinear elements generate new frequencies when signals pass through them? A mixer exploits this directly.
So you feed two signals into a nonlinear device.
Correct. A mixer takes two distinct input signals. The actual radio frequency signal you want to process, let's call its frequency FRF, and a signal from a precise, stable local oscillator, FLO. When these two signals interact in a nonlinear way, for example, by passing them through a diode with that nonlinear current voltage curve, or a transistor operated deliberately in its nonlinear region, they fundamentally generate new frequencies at the output due to the mathematical mixing multiplication that occurs.
What frequencies come out?
Specifically, you get strong components at the sum, FRF plus FLO, and difference FRF, FLO of the input frequencies. You also get harmonics of the inputs, 2FRF, 2FLO, etc., and other intermodulation products like 2FLO, FRF, etc. It can be a whole zoo of frequencies.
A zoo, so how do you get just the one you want, like the IF?
That's where filtering comes in immediately after the mixer. A filter, typically centered at the desired intermediate frequency, FIF, meticulously selects only the desired sum or difference frequency. Example, the difference frequency FIF will quote FRF, FLO for a down converter, and aggressively rejects all the other unwanted frequencies, the original inputs, the sum frequency, the harmonics, everything else in the zoo.
So the magic really is in that controlled nonlinearity, creating the desired sum difference frequency, followed by aggressive filtering to pick out just that desired band. What are the different types of mixers engineers use, broadly speaking?
We can broadly categorize them as passive or active, and then further by their specific configuration which affects their performance. Passive mixers typically use nonlinear elements like Schottky diodes.
Schottky again, for high frequency.
Exactly, because of their excellent high-frequency performance and that crucial lack of diffusion capacitance, making them ideal for microwave applications. The main characteristic of passive mixers, though, is that they always introduce some conversion loss.
Loss. The output is weaker than the input.
Yes. The output power of the desired IF signal is always less than the input RF signal power. We express this as a gain less than unity, or a positive loss in decibels, kp0 dB. This conversion loss is a key design consideration for any system using them, as it directly impacts the overall noise figure of the receiver chain.
Okay, passive means lossy. What kinds are there?
The simplest is the single-diode mixer. While straightforward to implement, it suffers from several disadvantages. It produces many undesirable intermodulation products, those unwanted frequencies in the output spectrum, which can cause interference and make filtering harder. And it tends to have higher noise, partly because noise from the powerful local oscillator signal can easily leak through or get converted down into the IF band, degrading the signal you care about.
So simple but noisy and messy.
Pretty much. To combat these issues, balanced mixers were developed. These typically use two diodes and a clever combination of transformers or balloons, balanced to unbalanced converters, to manage the signal phasing. Often the local oscillator signals are applied in phase to the diodes, but the incoming radio signal components are applied out of phase, or vice versa.
Why does that help?
This balanced configuration inherently helps to suppress or cancel out certain unwanted components in the output spectrum, especially the strong local oscillator frequency itself and some of its harmonics, and also reduces the noise contribution from the LO. The result is a much cleaner output spectrum with fewer spurious signals, making the subsequent filtering easier.
Better suppression, and I assume it gets even better with more components, like double balanced.
Indeed it does. The pinnacle of passive mixers, widely used in high-performance systems, is the double-balanced mixer, often called a ring mixer because it uses 4 diodes arranged in a precise ring or lattice configuration driven by carefully balanced transformers. These offer even better suppression of unwanted frequencies. Both the local oscillator and the input RF signal frequencies themselves are suppressed at the output port, along with many even-order distortion products.
Wow, cancels both inputs.
Ideally, yes. And they result in even lower noise conversion. Our source states that with a cubic approximation of the diode's characteristic, a common simplification, ideally, only the desired sum and difference frequencies are present at the IF output port. This makes for a very clean output, significantly simplifying the filtering requirements downstream.
Okay, double balanced for best passive performance. What about active mixers? You mentioned they use transistors.
Right. In contrast to passive mixers, we have active mixers. These cleverly use transistors like MESFETs or HEMTs for microwave frequencies as their primary nonlinear elements, operating them in a way that promotes mixing.
What's the big advantage of using a transistor?
The absolutely key advantage here is that they can provide conversion gain, kp 0 dB. This means the output intermediate frequency signal can actually be stronger than the input radio frequency signal.
Gain instead of loss. That sounds huge for weak signals.
It is. This is absolutely critical for receivers dealing with very weak input signals, as it boosts the signal early in the chain while performing the frequency conversion, significantly helping the overall signal-to-noise ratio of the entire receiver compared to using a lossy passive mixer followed by an amplifier.
How do they configure the transistor to mix?
The source describes different sophisticated ways to apply the input RF signal and the local oscillator LO signal to the transistor's terminals to induce mixing. For example, both signals might be applied to the gate, or one to the gate and one to the source, or one to the gate and one to the drain. Sometimes they even use the inherent nonlinearity to mix with the second harmonic of the LOO. Performance-wise, models in the source show impressive conversion gains, potentially over 7 dBs for microwave active mixers, with optimal local oscillator power typically under 10 dB, 10 milliwatts, which is a very reasonable power level for an LO signal.
So active mixers give gain, which is great. Any downsides? Maybe linearity.
That's often the trade-off. A critical parameter for all mixers, but especially for active ones which handle gain, is their linearity. This is often quantified by P1 dB, the 1 dB compression point we mentioned briefly before.
Yeah.
It's the input RF signal power level, where the output IF power is 1 dB less than what you would expect if the mixer were perfectly linear.
So it measures where it starts to significantly distort or compress the signal.
Exactly. It's a very important measure because it tells you how strong an input signal a mixer can handle before it starts to generate significant distortion products, like intermodulation, that could interfere with your desired signal or other signals in nearby channels. A higher P1 dB indicates a more linear mixer, capable of handling stronger input signals without distorting. There's often a trade-off between achieving high conversion gain and maintaining good linearity, high P1 dB, in active mixer design.
It's absolutely fascinating how the precise choice of components, diodes versus transistors, single versus balanced versus double balanced, and their arrangement and biasing can dramatically change the performance characteristics of these frequency converters, especially that delicate balance between gain or loss, noise, and linearity. It truly shows the ingenuity required to make our connected world work seamlessly. X, the ongoing evolution of transceivers and a provocative thought. Wow. This deep dive has truly unpacked the incredible complexity and sheer ingenuity behind radio transceivers. I mean, from managing minute noise fluctuations that feel almost invisible, to generating incredibly stable and precise frequencies using oscillators and synthesizers, and then skillfully converting signals across vast stretches of the electromagnetic spectrum with mixers. It's clear that every single step involves a constant battle of engineering trade-offs and relentlessly pushing the absolute boundaries of physics.
It absolutely highlights how fundamental principles of electronics, physics, and advanced material science all converge to create this invisible infrastructure that underpins our connected world. And the source really emphasizes that while many modern radio systems now rely heavily on highly integrated, pre-designed integrated circuits, where much of this complexity is hidden away inside tiny black chips.
The black box approach.
Right. But understanding these underlying principles, the physics of amplification, oscillation, frequency conversion, noise management, impedance matching remains absolutely critical. It's essential for true innovation, for efficient troubleshooting when things go wrong, and ultimately for pushing the next generation of communication technologies beyond what we can even properly imagine today. You can't innovate if you don't understand the fundamentals.
So what does this all mean for you, the listener, navigating a world increasingly reliant on these invisible waves, often without giving them a second thought? What's the takeaway?
Well, I think it means that every single time you make a call, stream a video, use your GPS, check your Wi-Fi connection, or simply listen to the radio, you're relying on an absolute marvel of engineering that operates right at the very edge of physical possibility. And the quest continues. The relentless pursuit of even higher frequencies, tens, hundreds of gigahertz, even pushing into the terahertz range, even lower noise approaching theoretical quantum limits, greater efficiency to reduce energy consumption and manage heat, and higher linearity for crystal clean, undistorted signals continues unabated every single day in labs around the world.
It never stops improving.
Never. Each tiny improvement in these fundamental transceiver devices unlocks vast new possibilities in how we connect, how we share information, how we sense the world, and how we interact with everything around us.
And perhaps this raises an important, maybe even provocative question for you to ponder long after this deep dive. We've seen how miniaturization and the relentless drive for higher frequencies lead to components acting less like discrete, identifiable parts with wires connecting them, and more like lines of transmission or integrated structures within the very silicon or gallium arsenide chip itself.
The lines are blurring, quite literally.
Exactly. So if our devices become so incredibly integrated, with components almost indistinguishable from the interconnections themselves, and our signals operate at such incredibly high frequencies that they start behaving almost like light, what new fundamental limits, or perhaps what completely unprecedented possibilities, will we truly encounter in the next generation of communication? And what will that ultimately mean for how we perceive and interact with information when it's flowing around us at terabits per second through devices smaller than a grain of sand? It's a future unfolding right before our eyes, built on these intricate, almost invisible foundations we explored today.
It's a field that constantly pushes the boundaries of what seems possible, fundamentally shaping our future in ways we are only just beginning to grasp. The physics gets weirder, but the potential gets bigger.
That was a truly deep dive into the hidden world of transceivers. Thank you so much for guiding us through that complexity.
My pleasure. It's fascinating stuff.
And thank you for joining us on this exploration. We hope you feel much more informed and perhaps a little more amazed by the hidden complexities that make our connected world possible. Until next time, keep digging deeper.